going to give a very brief introduction to quantum networks, especially the engineering problems, the implementation problems, challenges of quantum networks. So my name is Guilherme Temporão. I'm associate professor at the Center for Telecommunication Studies of the Pontifical Catholic University of Rio de Janeiro. So the first question is why quantum networks? Well, I would ask it on the opposite, why not? Because there are many applications that can profit from quantum networks. We have, for example, the most straightforward example is quantum communication, quantum key distribution, for example. Quantum key distribution is actually a protocol that was created for point-to-point communications. Like one person, Alice, is trying to share a secret key with a second person, Bob. But of course, they not necessarily have a continuous path, a channel link, a direct link between them. So when they are in a certain network configuration, of course, quantum networks come into play. We have also many kinds of distributed quantum or classical cryptographic protocols that could profit on quantum networks. And we also have distributed quantum computation, like have many quantum computers that are interconnected in a network, and different quantum computers do a different part of a certain quantum calculation or simulation, for example, or have more traditional kinds of client-server quantum computing and so on. So, of course, for distributed quantum computation, you will need a quantum network. This is really something that we cannot live without it in the future if we want our quantum computers to integrate and to perform tasks together. And you have also some tasks of sensing. Like, for example, there are some protocols of clock synchronization that are really interesting. They use entanglement, or you can combine telescopes, do some interferometric, even some fundamental tasks of quantum mechanics, like some Bell violation test without any loopholes, like has been performed a few years ago in a scenario which was kind of a quantum network. So there are many different possibilities for use of quantum networks. So in a quantum network, we have both the transfer and sharing of quantum information, say qubits, between multiple users. So of course, the first naive idea for a quantum network would be to have direct transmission lines between all nodes, which is of course unfeasible if the network is very large, because we will have many nodes, and this would require an exponentially large number of links. However, this is not the only drawback. There's also another problem, which is photon loss, especially if the distances are really high. I mean, for really long links, there's a problem with photon loss. If you take, for example, optical fibers, which have a minimum attenuation of 0.2 dB per kilometer, a minimum attenuation coefficient for 1550 nanometers, then, for example, if you take a link of 100 kilometers, you have already a 20 dB loss. If Alice sends 100 photons to Bob, in average, Bob will receive 1 photon. If we increase a little bit this distance for 250 kilometers, for example, now I have 50 dB, which is much worse. 1 over 100,000 photons sent by Alice will reach Bob. And certain protocols, of course, will fail. And the classical solution to this problem is very straightforward. Okay, there are many losses. We use repeaters or regenerators. Yeah, this is a very straightforward solution. Okay, for classical optical communications. But in the quantum scenario, it doesn't work like that. I mean, how could we think about the photon amplification? How can we amplify 1 photon? I mean, when you talk about amplification, we're talking about taking 1 photon and create copies of this photon. That's what, for example, any optical amplifier does. Yeah, it takes a few photons and the output to have more photons. However, you cannot do perfect copies of a single quantum state, a single arbitrary quantum state. This is exactly the no-cloning theorem by Wouters and Durack. So if you have an unknown quantum state, you cannot do like a clone of a perfect clone of this state. And of course, the reason, if you think physically on the amplifiers, is spontaneous emission. You can't have an amplifier without spontaneous emission, so you cannot do like a perfect clone of an input photon. So what about photon regeneration? Can't we use some kind of regeneration in this network? And the answer is, well, yes, but if we perform a regeneration, that means that we make some measurement, and a measurement will destroy the original quantum state. And here it's very important for you to understand that usually what we are dealing with here is the transfer of unknown quantum states. Because if I know my quantum state, I can just pick up the phone, call Bob, and say, hey, Bob, prepare a certain state. I have no need for transmitting a state that I know beforehand. So most of the states here are unknown quantum states. But we cannot use this for most applications. So the bottom line is classical communication network solutions do not apply this scenario of quantum networks. So we have some first tries to solve this problem. We can have a network of trusted nodes. That's exactly what China did when they constructed that quantum network backbone from Beijing to Shanghai a few years ago. So actually what they have, this is a very long link, right? It's about 2,000 kilometers. So it's impossible to send just single photons from Beijing and expect them to arrive in Shanghai. And so what they did is they put 32 trusted nodes along the way. So they kind of divided this link into smaller parts. And well, so what happens is actually you have point-to-point connections between each of these two consecutive nodes. So each node kind of regenerates the qubits and sends them to the next node. However, if we think about some applications, especially the applications that they have in mind, which is quantum key distribution, if one of these nodes is compromised by an eavesdropper, let's say, so the whole system becomes vulnerable. So when you think about QKD, well, yes, we can use this approach of trusted nodes, but in this scenario of cryptography, usually no one trusts no one. So it's kind of difficult to play with this scenario. Okay, but of course, it's much better than nothing. It's much better than the classical protocols. And as far as I know, they didn't use the full implementation of QKD, okay, which uses QKD and one-time pad. And for the one-time pad, you need the key to have the exact same size of the message. So this would require a very high bandwidth. And I believe this is not the case for the moment. I think they are mixing QKD with some private key cryptographic protocols. I mean, they reuse the key a few times before renewing the key. But of course, this is a problem for all networks, okay, not just trusted node networks. In this scenario, as you can see, it does not apply to all quantum networks, to all quantum tasks. You have some tasks that the nodes don't really trust each other. They are like adversaries. So in this scenario with adversary nodes, of course we cannot have trusted nodes. So what we do, a better solution, of course, a much more complex solution, is using entangled states. So instead of using intermediate nodes and recovering the information, we distribute entanglement across the network. So once you have entangled particles between two nodes, then you can send quantum states from one node to another using the quantum teleportation protocol. So the main idea of a quantum network is actually distributing these entangled states. And an entangled state is a certain kind of state that where the collective property of the state for a specific degree of freedom is well known. For instance, in this case here, you have two electron spins, and you know from the state that they have opposite spins with a certain phase relation. But if you look into just one of the spins, they have no real value. I mean, there's no physical reality associated with the individual spins. So this is what a maximally entangled state looks like. And so if you have like a large quantum network, as we call it a quantum internet, I mean, a network that interconnects smaller networks. So it will only work because of these large distances if we distribute entanglement between nodes. And it's important to realize here that this distribution is made beforehand. I mean, it's not the distribution of quantum states that is the communication itself. You previously distribute entanglement, and then once you have entangled particles between two nodes or more nodes, then you can make some quantum network tests with these entangled states. So this is a problem of making possible this distribution of quantum states, of entangled states over the network in a fast and reliable way. So how do we do this? How do we distribute entanglement? We use the so-called entanglement swapping protocol, which starts with individual entangled states, which can be distributed by direct transmission. Let's say Alice generates an entangled photon pair. She keeps one of the photons for herself and sends the other photon through an optical fiber, for example, to Charlie. And so every elementary link does that. And then what an intermediate station does, like intermediate node, Charlie in this example does, it performs a Bell state measurement, which is a projection of these two photons or other particles into one of the four Bell states. So once Charlie obtains a successful Bell state measurement, it communicates the result. I mean, Charlie says to Alice and Bob, look, I got here the result phi plus or the result psi minus, and so on. And then Alice and Bob can do some local operations and recover entangled state. Of course, this won't be a pure entangled state, a maximally entangled state, so it needs to do some tasks afterwards, like some entanglement distillation. But this is another problem that I won't have time to talk about that. So the element of the network which is responsible for extending this entanglement is called a quantum repeater. So the task of the quantum repeater is to perform this kind of Bell state measurements, these entanglement swapping tasks and creating entanglement between distant nodes. So you make multiple entanglement swapping steps. And of course, if you take all these steps at the same time, the probability of success will be really, really low. So these quantum repeaters need some kind of quantum memory. I mean, once you get a successful Bell state measurement in one of the nodes, it must wait for the others to all herald that they got some result, and then, I mean, there's something in their quantum memories, and then they can do this entanglement swapping. So this is one of the main problems of quantum repeaters. They need quantum memories. And of course, there are still many technologies being researched for what's best for every kind of scenario of every possible quantum network. And if we think about this entanglement generation as some kind of resource for quantum communications, then what we need here is some kind of multiplexing, because we don't have to try one entanglement at a time. We can do it like multiple tries at the same time, for example, using spectral multiplexing. And how can these states be transferred in each elementary link? So we have this kinds of encoding in some degrees of freedom of photons. We have polarization states, for example, which are kind of natural states for qubits in photons. Okay, so if you take, for example, the horizontal polarization is a 0 and the vertical polarization is a 1. So we have some kind of a superposition of vertical and horizontal polarization. You can have all possible qubit states. And for optical fibers, it's really easy to change, to do some rotations here in Blocksphere between those states, especially if you want to do this automatically. There are many devices like lithium niobate polarization controllers that can respond to gigahertz. So this is a possibility. And but for optical fibers where we have birefringence, you can use a much better approach, which is kind of immune to polarization fluctuations, which is the time beam encoding. So use an unbalanced Mach-Zehnder interferometer where the time difference between the two arms is larger than the coherence time of the photon. So you can have a kind of superposition here in the output between the early mode, which is the photon that took the short path, and the late mode, which is the photon that took the long path. And it's possible to show that this is equivalent to polarization state. It actually can map one into another. So these are the degrees of freedom that we usually employ for photons. And the quantum channels are exactly the same as the classical channels. You have free space transmission, and you can have optical fibers. So each one has some preferences and some drawbacks. It depends on the condition, the distances, and so on. But if we are talking about very long distance communication, most of the time we'll be talking about optical fibers, and of course sometimes satellite transmission, for example, which goes through free space. So when we talk about a quantum network structure, we have to have some elements in this network, and in this proposal here by one of my colleagues, we have different elements that have different kinds of intelligence in the network that can deal with different kinds of requests and work in a different way. So this entanglement swapping step is performed by this quantum repeater chain, whereas the storage of quantum information is performed in this in this node here, which is kind of a quantum router that will be responsible, for example, for choosing the best way for an entanglement be generated between node A and node B. So the technologies that are used in each of these elements is different. So actually we have a real challenge here for engineering, because it's not just one technology that can be used. Actually, we need many different technologies working together because the boundary conditions are completely different. For example, if you talk here about the quantum repeater chain, we are talking about telecommunication wavelengths, for example, because we need to overcome large distances. So the photons must travel along optical fibers, and telecommunications wavelengths are much better suited. But here, for storage or for interfacing with quantum computers, then maybe wavelengths close to the visible range are better suited. So we have to deal with this difference between each task and each technology, which is better suited for each task. So, for example, for these quantum routers, a good candidate is nitrogen vacancy elements. So it's possible to show that there's a recent Nature Photonics review that I ask you to have a look if you're interested. But it's possible to show that this kind of quantum memory, if you use, you have both the spins of the electrons in the vacancy, but you also have the spins of the nuclei of the carbon and the nitrogen atoms that are close to the vacancy. So these long-lived memories can reach hundreds of milliseconds if you do it correctly with dynamical decoupling and so on. So even at room temperature, it can have about milliseconds of coherence time, which can be good enough for many applications. And for other applications that need more time of storage in these memories, then you can go to lower temperatures. And they have shown some kind of entanglement between different NV memories here, using a kind of effect called the Hong-Ou-Mandel effect, which is related to the photon bunching effect. When two identical photons impinge on a beam splitter, they always go out in the same arm. So with this kind of a two-photon interference, you can erase which path information, and then you entangle the two NV. So you can have long coherence times, easy storage, and of course we need some interface because the fluorescence for NV is invisible. And as I said, many times we need something in the near infrared for communications. And then we have to use a different kind. I don't have time to talk about that, but we can use, for example, atomic frequency quantum memories using this kind of multiplexing, of frequency multiplexing. But I'm going to skip this because my time is up here already. So in summary, entanglement is the main physical resource for quantum networks. So the main challenge is to distribute entanglement in a sufficiently high rate and with a sufficiently high fidelity to these maximally entangled states. So for this, we need high coherence and high fidelity quantum memories, and there are many different technologies that can provide that. We need many kinds of protocols, for example, protocols for entanglement purification, so we can have these maximally entangled states out of entangled states that are not as entangled as they should for the applications. We need high brightness in the photon pair generation sources. So we have a really high bandwidth for generation of entanglement. And we need, of course, efficient interfaces between this flying and static qubits. I mean, the photons and this NV spins, for example. And there's a struggle now with the development of protocols for network management, because the quantum network is like a classical management. It needs protocols, and we need to define names for nodes and routing and so on. So it's really challenging, and the research is really intense right now. So thank you very much for your attention.